Anthony Williams. You decided to speak on software and safety,
yes.
And I'm looking forward to hear from you about this. It's very much, you're setting the theme of the conference. And so, let's get started.
Okay, let's get started, yes. So yeah, so as I said already, I currently work for Woven by Toyota. We're writing low-level C++ libraries for automotive. And in doing that, then I really appreciated what's involved in writing software that there's real safety concerns about what happens with this. And it's not something, it's something that I've looked at other points in my career, but not quite so deep. And so then I've been thinking about that, and it's something that's actually dominated quite a lot of my thinking outside of my paid employment as well. So I'm going to start today with some definitions. The important one for lots of things is safety-critical software. This is software where if the software goes wrong, then somebody could be injured or die. And so for this sort of software, we have a lot of serious constraints, high-level standards and about what we should do, how you develop that. And so, but the point is that it then encompasses a lot of things, and it's important to understand that the way we approach developing that sort of software can be different from other things. But then, if you think about things more widely, then there's also lots of things which have software that has consequences for safety in some way. Particularly if you're thinking of, you're not somebody directly involved in the software field, then the things that have consequences for people's quality of life. People will talk about keeping their money safe, being safe online. You might have to think about whether you've got something. If the software goes wrong, is that going to cause somebody to lose their money? Is it going to cause them to loss of trust? Is it going to just cause them to lose a couple of days' work? And also then potential for identity theft or being used, have your software compromised and therefore used as part of a botnet or something. So if you think about things more widely, then there's a lot of overlap between safety and the way that we do things for safety-critical code, and then security and things like that, and how that affects lots of software in the wider ecosystem. So what sort of software are we talking about? Well, obviously, at the safety-critical end, software for dangerous things. Automotive control software. The software that helps, says when you turn the steering wheel, then it actually turns the wheels. That when you put your foot on the brake, then actually it applies the brakes to the car. Or controls the engine of the car. Or similarly, the software that runs in the cockpit of an aircraft. Then similarly, it's a big piece of dangerous equipment. And if the software that's controlling it goes wrong, then it's going to have real consequences. And likewise, factory equipment. Similarly, you've got a big robot arm in a factory, then you want to make sure that it goes where it's supposed to go and doesn't swing around and injure somebody. Or even power plant software, particularly nuclear power plants. If the rods need to be lowered into the power plant to slow down the reaction, and the software goes wrong and it lifts them out and makes the reaction go stronger, then this is going to be pretty bad. So there's a lot of things. If you've got software for dangerous devices, you really need to pay attention. And similarly for other things, then like medical devices, if you've got a pacemaker, then if your pacemaker goes wrong and it makes somebody's heart beat at 200 times a minute, then that's probably going to have bad consequences for them. Or if somebody's already having a heart attack and you put a defibrillator on them and the software makes it go wrong, give the wrong voltage or whatever, then also bad. Or artificial lungs or scanners. You don't want your CT scanner to put the dose of X-rays too high or something like that. So again, this is safety-critical software. The consequences of things going wrong are directly impacting people. But then there's things which are well, they're less direct consequences. But they're there. The reason that we have this software is in order to increase safety. And so, to a large extent, the same sorts of things apply. Now, if you've got driving assistance software, then if you start relying on the software to keep the distance between you and the car in front, and it goes wrong, and it doesn't notice that you're now catching up with the car in front, and then you are relying on it, and you don't notice, then now you might actually get involved in an accident and things, and that's bad. And likewise, if you rely on the driving assistance to keep you in lane, and so it gives you some control over you give the car some control over the steering, and then it goes wrong and it steers you into the central reservation or the car next to you, then again, this is bad. So the same sorts of standards need to apply to these sorts of things. And the same care and attention. And even household appliances, if you've got an oven or a stove that's supposed to cut off when it overheats, and it doesn't, but you start relying on that, then that can have consequences. You can have a fire in your house. Things can be bad. Or fire alarm and a sprinkler system. It itself, the actual effect of the sprinkler going wrong in itself doesn't cause a problem, but it might mean that now there's a fire that doesn't get put out because the sprinkler didn't start. And so that then has consequences. So you need to make sure that these things are working, and they work as intended. And so you have to apply the appropriate levels of design and thinking and testing. But then, if you keep thinking, then you find, well, no, what about other things? Traffic light control software. Again, the actual turning on and off a traffic light probably doesn't have any direct consequences. But if all the lights at an intersection are green at once, you're probably going to get an accident. And likewise, with air traffic management, if the people who are making the decisions about which planes get to fly where don't have the correct information because the software's gone wrong, then you can have accidents on trains. These sorts of management of people who are in control of dangerous equipment. It's helping. If you need to make sure that gives the people who are making the decisions the right information. Or even personal data. I said earlier about we want to think about the consequences for identity theft and things like that. So if you're making payment software, all the time we all use electronic methods of payment. If that goes wrong, then potentially we could lose money. The people who we're paying could lose money. Just as a simple example, recently, my son was trying to make an insurance payment, and he does it online, and then his bank says, yes, I've made the payment. The insurance company says, no, I haven't received it. And so the insurance hasn't, they said, we can't give you the insurance because the payment hasn't gone through. And so there are real consequences for simple things like payment software going wrong. Or actually, in the banking software, I'm sure we've all heard the news about software of automatic trading where banks lose loads of money because there's a trading system that made trades it wasn't supposed to have because something was out of range or whatever. There are real consequences for things that aren't. They're not immediate life and death. They're not safety critical, but actually there are still consequences. Phone software. We use phones all the time for all sorts of things. There's a lot of our personal data goes through our phones. Potentially, that could be compromised. There's a real security issue there in terms of how being able to lose your data. And so the same sort of principles apply for those sorts of things. And the same again, social media. Lots of things come through social media, and if your social media account is compromised, then that can actually have quite a big effect on your life. in terms of losing access to people, or the scammers having access to personal information they can use to extract things from you. So we need to pay attention to actually the same safety principles apply in lots and lots of areas of software. Even things like games. If you've got an online game, then that then exposes your computer to the internet and therefore can potentially be compromised. You can get potentially have a security access there. Even daft things that like if you use an online game and you've got a password on it and you happen to use the same password there as somewhere else, which is bad password practice, but lots of people do it, and then the game gets hacked and your password there is compromised, and now people can use that to try and hack your other parts, hack your bank accounts or whatever. And so, and again, internet-connected devices, you have an internet-connected widget that's attached to your fridge or just attached to your lights so you can turn them on and off from your phone or whatever for convenience. And if that gets compromised, part of a botnet, then again, it's not so good. It doesn't necessarily have an immediate impact on you, but then it's still the same sorts of principles around safety. And web browsers. Everything happens through a web browser. If the web browser itself is compromised, there's bugs in the web browser, then that leaves, it doesn't matter how good your online banking is if your web browser leaks all your passwords and everything because it's been compromised itself. Even spreadsheets. And I say even spreadsheets because you might think, well, it's a completely self-contained offline piece of software. But actually, spreadsheets drive a lot of business. And so if there's actually bugs in the spreadsheet, then that can cause all sorts of downstream problems because if people don't realize them. And the maths that gets done in spreadsheets is often is quite complicated for the people using them. It might have been carefully set up by somebody who really understood everything and they could double check it. But these days, the person who's using it doesn't do that double checking. And so if it goes wrong, then there's consequences. So I said at the beginning, for actually safety critical stuff, then we have real standards. The baseline standard is IEC 61508, Functional Safety of Electrical, Electronic, and Programmable Electronic Safety-Related Systems. It's a sort of all-encompassing thing for anything electronic. But for most industries, then there's a specific standard that then is sort of based off that. For automotive, which is the one I'm most familiar with, it's ISO 26262. For aerospace software, it's DO 178C. For medical software, then there's a whole set of standards, I believe, based on IEC 62304. And for railways, then Senelec EN 50128. And then, of course, other industries and, like I say, everything, the IEC 61508 covers everything electronic, and then there'll be something industry-specific for anything that matters. But the thing is, if your software doesn't come under the safety-critical banner, then technically these standards don't apply. But you should still consider the safety and the security, the potential impact of failure of your systems. Just because your game isn't directly going to impact somebody's life doesn't mean that you don't need to worry about the consequences of it going wrong if it's got any form of internet connectivity in there that where there could be a security issue that could then lead to consequences for people. Okay, so these are sort of why we care. But then what are the actual things that cause us problems? And to be fair, the biggest cause of problem is things that we didn't expect to happen. The unknown unknowns of the world. And sometimes they're just the things that we thought, well, this is never going to happen. Nobody's ever going to need more than 640K of RAM. We're not going to overflow time T in 32 bits. That's just not going to happen. Our computer won't be around long enough for that to be an issue. So there can be things that we think won't happen, and then eventually they do. And so that's one way that we get problems. And the other thing is the things that we really just didn't even think that was a possibility. It just didn't occur to us. And that one's really hard to deal with, because it's all very well saying, think harder. But no, I'm sure you've all tried to think harder about some things, and it doesn't give you the inspiration to realize what the out-of-the-box way of approaching this is. And so that's just a really hard thing to deal with. And we need to accept that there always will be things that we didn't consider as possibilities. And so we need to have, overall, when we're doing our designs, then you need to think, what if something I didn't expect happens? Which is, again, it's a hard thing to think, but you still need, particularly as you go towards the more safety critical side, you've got to have that sort of, it's the belt and braces approach. Well, this should work, we shouldn't have a problem with this, but just in case that we're going to check, we're going to have a backup, we'll have a secondary system, all sorts of things like that. And then, of course, the other big cause of mistakes, of problems, is just genuine mistakes. The developers intended for something specific to happen, but then we coded it wrong, because we're human. We just genuinely make mistakes. And we commonly call these bugs. And generally, one aspires to there not being any bugs, and we try to set up our software development processes to reduce the number, but, like I say, inevitably, we're human, and these happen, because there will be some scenario, some corner case that we didn't think of that specific scenario, and yes, it's supposed to happen, that all these things are supposed to happen a specific way, but, and we code it up so under normal circumstances, it does happen that way, but there'll be some corner case that we didn't think of, and so then we've got a bug. And then, of course, there's all the other things. There can be actual genuine hardware failure. The problem is not the software itself, but something went wrong with the hardware. That could be that there was the motor just burnt out. It could be that the sensors, just something in the way. It's got some dirt on the sensor, so it can't genuinely give you a valid reading. The display, one of the pixels might have gone faulty on the display, or or something else, or the storage might have worn out because you've written to the same part of your flash storage too many times, and it can't do anymore. There's all sorts of things that can actually physically go wrong. And then there's just bad input. You get a corrupt network message. Sometimes you might be deliberately corrupt network message because in trying to exploit a problem in your code. It might be that the user, you're faithfully following what the user's intending your car to do. They try and steer you off a bridge. Now, obviously, if you're writing software that's trying to keep the car safe and keep it on the road, then you need to say, well, hang on a minute. We're steering off a bridge. Maybe we shouldn't be doing that, and put up appropriate warnings and beep at the user and maybe steer them back on the road or whatever. Or if you're on a medical thing and the doctor enters the things wrong, they miss a decimal point, or they type two buttons because they're next to each other and they don't realize, and so suddenly they've got 10 times the amount or whatever. So you might, these can cause genuine problems. And so if you're thinking about the software and what its intended use is, it's like, is there safeguards we can put in that deal with this bad input? Range check it. Check what the environment looks like, that sort of thing. And obviously, if you're thinking about it from a safety point of view, then these are design issues. It's like, these things are going to happen. We will get bad input. We will get hardware failure. How can we make our system cope? Can we design the system to handle these issues? And so then I move on to my next definition, which is undefined behavior. Now, this is a quote from C++ 23. Behavior for which the document imposes no requirements is what the definition in the standard says. And that means that from the point of the C++ standard, there's no requirements on what this does, so it can do anything. And usually, in practice, for lots of things, then what that means is, something relatively straightforward from the CPU's point of view. There's a straightforward, what should I do with this code when the compiler assumes that this is undefined behavior. But the thing is, and so therefore it can just, we'll just do whatever happens. It says read off the end of this array. Well, no, the undefined behavior says anything can happen, so we'll just give you the value that was there and assume that it was a valid object. And that's the sort of thing that leads to problems, because anything can happen. The compiler and the runtime library aren't going to deal with the scenario that what happens here, and so then you get random things. Code that you never expected to run now runs. And so you get security problems and just bad results in all sorts of ways. And certainly if you're thinking about safety, then you need to think that it could do anything at all. Really is, it can do anything at all. So ISO 262 says, amongst other things, the implemented software unit shall be verified and provide evidence for confidence in the absence of unintended functionality. As in, your code should not do anything you don't want it to. And you need to provide evidence that that's the case. Now, given that undefined behavior can do anything at all, then that's likely to include something you didn't intend it to do. And so you need to avoid undefined behavior and do your best. And then, because this is a safety-critical system, you need to provide evidence that there is no undefined behavior in this code, which is somewhat tricky, but it sets a high bar, and that's where you need to go. And again, for safety-critical stuff, you need to provide the evidence, but for any other software where there's any safety consequences, maybe you ought to be thinking about this too. Can we avoid undefined behavior? What can we do about it? Now, there's been a lot of new stuff in the news about memory safety. And whole reports on the case for memory safety and why you should be switching to memory-safe languages and stuff like that. Memory safety is a big problem. Well, really, these are just examples of the consequences of undefined behavior. It's undefined behavior due to lifetime errors. It's undefined behavior due to bounds errors. And so really, it's just, you encompass the whole thing. Memory safety issues, it's just undefined behavior. You still need to avoid it. You use the same sorts of things to think about it and deal with it. And mostly, again, this comes back to our unknown unknowns. Undefined behavior is a consequence of an unexpected event. You got a value that's supposed to be in range, and it isn't, and so you go off and read out of range, and then random things happen. And so, again, if we're being serious about safety, then we need to work hard to ensure that these unexpected events somehow get eliminated. They get incorporated. They get moved from unexpected events that we don't know how to handle to expected events that we have a plan for what to do. That's what we're trying to. That's what we're trying to move the needle. We're trying to move from things being unexpected to something for which we have a plan. And the thing is, all this, it fundamentally affects how you develop your software. Because if you're just sort of trying hard to do our best under normal circumstances, then you don't necessarily think through all the consequences. You don't spend the time to test every single possible input, and things. So you start having to once you take on board that actually there are all these things that we need to avoid, and we really need to prove that we're avoiding them, then that changes how you do things. It changes how you specify your software. It changes how you test your software. So, just for example, and I said, bad input, one of the problems. And so, a tester walks into a bar. What are they going to do? Maybe they'll order a beer. But hey, they're testers, so they'll order 99 beers. Or maybe an orange juice. Or perhaps -1 beers. Or maybe even 4 candles. Or a drop table drinks. you need to cope for all these sorts of random inputs and think, what is the valid input that's going to happen? And for every possible input, you need to have an intended behavior. And that doesn't mean that it needs to do something useful. No. If somebody orders -1 beer, then the bartender's not going to say, fine, give me a beer and I'll give you some money back. They're just going to say, I can't do that. No. And that's reasonable. The point is you have to have a system that works around that deals with what are you intending to do here. No. And the thing is that every possible input includes a whole bunch of things. It includes all the network traffic that your code might have to deal with, any content that you're reading from files, any interactions with any external system in any way. No, this is all possible input. And so that's a lot of things you need to think about. And so that's a design problem. It's like, how do we deal with all this universe of input into our program in a way that make sure we always have an intended behavior? The CrowdStrike failures. It's like the config file was in a system. They didn't expect it to have this, and therefore they didn't have an intended behavior for what the config file, when the config file looks like this, what do we do? It's like, who knows? And the answer was, crash all the computers. And that clearly was not what they wanted to happen. But because they hadn't designed for it, it did happen. And so we need to design all our interactions so that our input is checkable. Now, if you've got a way of specifying the structure before interpreting the values, then we should do that. Now, use checksums to validate your input. And use a schema to check the format, whether that's an XML schema, a JSON schema, just a binary schema that says the first 2 bytes specify this, the next 2 specify that, and the total length is this value. It's like, well, if you've got a way of checking, does the piece of data that I'm processing have the right form and structure before you actually look at what the values are, then that gets you a good way ahead of being able to validate things. Validate the sizes and offsets. The packet says it's 2K large. The offset says go to the offset at 4K. It's like, no, that's out of range. No. If I was supposed to go to the 4K offset, the packet should have said that was that big. Just check these things. And then you decide what to do if you've got invalid input. Sometimes that's just, oh, well, we can ignore that. Sometimes it's like, well, I've got to do something, and I've been given a bad value, what do I do here? And so you need to choose what that something is. Maybe there's a default you can do. Maybe the answer is put up an error message. Depending on the context that your software is running in, what that something is will vary. But you need to decide what it's going to do. And that's the tricky part. What if the input is invalid? What do we do? What if the input is a valid input to the system, but we shouldn't be getting it now? In the current state of the system, you shouldn't be saying do that. You're controlling a robot arm, and you can send it a command for moving up and down, but you shouldn't be sending that when it's over there. And so it's like, well, fine. Is this a valid input now? So that's a separate thing to think. And then what if the input is that actually, that sensor over there doesn't work anymore? It's giving me an invalid value. So how do I deal with the fact that my system has a sensor in it that doesn't work? My car at the moment has I must have driven through some mud, and so every time I get in the car, it turns on and says, the parking sensors aren't working. I get big messages all over the thing. And that's fine. I now know that the system's not working, so I'm not going to rely on it. I can look around. Whereas if, on the other hand, it didn't give me that error message, it just silently said, oh, I'm not detecting anything nearby, so clearly there's nothing nearby, I'm not going to warn you about it. And then I didn't pay attention to the fact that I was close to a wall and scratched my car, that wouldn't be so good. So you need to think about, some of the input is, this other bit isn't working. And how do we deal with that? And overall, if we're thinking about safety, we need to design our whole system so that all these things suddenly become expected values, and we have expected behavior that makes the system work gracefully. Even if that is less well than it would do if you're giving me good input. But overall, it's still, we keep running in a reasonable fashion in some way. Or do something meaningful anyway. Sometimes it's just, well, given this input, I can't do anything, sorry. And that's a valid thing to decide, that's what your software is going to do. But you've got to make that decision and tell the user as a consequence. And then, of course, having made all these decisions and thought hard, we've now got to test it. And the thing is that then malformed and invalid inputs can vastly outnumber the potential of valid things. You're allowed an input, and it's a number, and it's okay, it's between 1 and 5. There's so many more numbers that are not between 1 and 5. So you need to start a way of classifying things. This comes back to the structure and schemas. It's like, can I quickly check is my input at all valid without having to exhaustively test everything? Because that's usually just an impractical problem. And so we need to do our white box analysis. We should feed our tests by looking at where we can see that there might be problems coming. And then we can help fill the holes. And so we can test all of our layers. Overall, everything that we do, every step that we do, we're going to miss something. There's going to be a lot of holes in our testing block of cheese. But if we make sure that it's thick enough that the holes don't go all the way through, and rather than the left-hand side of the piece of cheese is opaque, but the right-hand side where it's thin wedge, some of those holes go all the way through. So we need to try and make sure that we have enough approaches overall to mean that we're testing the whole system and making sure that from the end user's point of view, everything works. Even if, so at some layer, it's like, well, the low level, well, we've done our best to test that, but it might have a problem. So in the middle layer, we assume, well, maybe there's a problem with the low layer, and that's one of the expected things is the low layer is not working. And then at the top level, then it's like, well, maybe some of the subunits aren't working. And we take those as expected values, expected inputs, is that things aren't working right. And then, of course, testing only gets us so far. Because one of the consequences of undefined behavior is it can do anything at all. And from my perspective, one of the most dangerous instances of anything at all is something that works okay when testing. And I've seen lots of places where this is genuinely the case. You run your tests and they pass. You run it on the production system and now everything breaks. And that is a problem, and that is one of the problems of undefined behavior. And you don't want that to be a safety critical system where everything's fine in testing, everything breaks in production. Because the undefined behavior is still there. And actually, memory safety issues, the reason why they keep hitting the headlines is because they often end up in this category. They run fine in testing because we don't test exhaustively everything, and there'll be some scenario where on the live system, then actually that has a consequence. And so we use static analyzers to avoid, tell you, you've got undefined behavior here on this line. Compilers are pretty good at this, actually. You often get warnings when there's obvious undefined behavior. Pointer equals null pointer. Do something with star putter. It's like the compiler will probably warn on that if they're right there on lines next to each other. But if they start being moved further apart, then the compiler itself doesn't have the time and complexity to do that analysis. So you use additional tools. We can also then use sanitizers, like address sanitizer, undefined behavior sanitizer, thread sanitizer. Run these at runtime. they make your program a bit slower, but that's because it's explicitly checking for undefined behavior in some form or another. And similarly, hardened standard libraries, where the preconditions on the standard library are then actually checked. This value ought to be within range. I'm going to check it, and I will terminate your program if it's out of range. That sort of thing. And they can help you identify some of this undefined behavior. So you should be running these in your testing. Often you can't run them all in production because they do add that extra overhead, and that has an impact on performance. But you certainly should be testing with all the sanitizers and hardened libraries you can get your hands on. And mostly, particularly with the hardened libraries, the overhead is sufficiently small that you can use it in production. I would assume that it's okay to start with and only then and turn off the hardening only if, A, you've not had any problems in production. No, you turn on the hardening, nothing ever breaks anyway in production, so it's all good. And B, you've demonstrated that actually there is that performance hit that you're willing to take that risk for. Certainly if you're safety critical, then you wouldn't, you probably can't ever feel confident to turn that off. But for lots of other places, then maybe you can. And this brings us into contracts. And so the hardened libraries check your preconditions, but that means you've got to have preconditions. We want a contract. What is required to be true when I call this function? And then vice versa, the post condition, what does this function then guarantee is true? And we can try and check these in code. Forever, we've been able to write if. If our pointer is null, then our precondition has been violated, and do something about it. And then we can process our pointer. In lots of places, we write macros that wrap this if. We say this is a precondition, and so you don't need to specify what happens when my precondition is violated because it's the same in every case. We call the precondition violation handler. And so we just have a precondition. It makes it easier to look in your code as well. There's so many places where you put an if that isn't a precondition, whereas you really should only be using precondition macros where there's actually a precondition that you're trying to enforce. So lots of places have this sort of approach. And this is what we use internally at the moment, because we don't have C++ 26 contracts yet. And that changes, it's not a macro anymore, it's actually a keyword. And actually, the curly brace has moved. For the macro, the curly brace is after the function declaration, because the macro belongs in the function body. With C++ 26, that curly brace is still after the function declaration, but the precondition is now part of the function declaration. And so you can put that on your, that is now something that is not part of the function body. It's part of the declaration of that function. And so in principle, therefore, it also can be checked by the caller in your code. And depending on which compiler you're using, it might well do that. And then the other thing is, of course, you can have things that your preconditions can be parsed by static analyzers. At the moment, then, CodeQL are shipping an experimental checker that if you annotate assert macros as it happens, the old C-style assert macro, if you put the requires comment before it, then the experimental branch of the CodeQL analyzer can say, oh, that's a precondition. I'm going to actually check that and verify and say, oh, well, if you run this code in this, then these inputs will mean that that precondition is violated. It can actually check that. I think you can also customize it so you can make that work with macros that you've defined. So your precondition macro I had a couple of slides ago, you can configure your the CodeQL branch to use those instead. So this is something that can, in principle, work today. And obviously, once the C++ 26 standard is ratified, static analyzers will start working with that syntax too. And so your analyzers can actually help with this. You say, this pointer must be null, and then it says, over here, you called it with a null pointer. Don't do that, and you can fix it. Lots of people worry about the cost of these precondition checks. Because if you actually just look at the code directly, I've got a precondition macro. There's an if in that. And so, yeah, well, No? On the right-hand side here, highlighted in red, that's actual assembly instructions that go with that. There is a cost. Obviously, if that check is not just, is it null pointer, it's something else, there's some function calls, maybe that is a bit more than 2 instructions. And obviously, that's all going to be, the check is on the hot path, but hopefully the handling is on the cold path. As you can see on the slide, then the compiler put the call to the violation handler in something that was marked .cold, because it's not. This is going to be moved. This is the cold path. It's not going to happen very often, because really you shouldn't have it. You shouldn't ever be calling the violation handler. If you call the violation handler, you have a bug. So we're aiming for no bugs. You shouldn't get there. So there is a cost, but the compiler is really good at optimizing it. So we have our precondition in foo that checks that the pointer is null, but then we call it from baz, which also has the same precondition, and now it checks it once. We're calling do something twice because that's what foo does, but we're not checking the precondition again. We still only have the one check. The compiler can see that. Obviously, this requires that it does the inlining, which it might be either directly because it's an inline function or at link time. So link time optimization can do this sort of an elimination. And so the cost is now less per call. It's like we've done three checks of this precondition, and it generated 1 bit of code. So this is good. But then actually, if you put it in a loop and the compiler can see the whole thing, it can eliminate all the preconditions. Our loop here goes loops through all the values. We're passing the address of a valid object. The compiler can see it's not null. It doesn't need to generate the code for that precondition check. So trust your optimizer in the first instance when you put these checks in. In lots of the cases, the optimizer is good. The people working on compilers spend all their time trying to eliminate unnecessary checks and unnecessary code. And it works. We can put extra checks in, and then the compiler will take them out again because they were unnecessary. So put the preconditions in, check them, and then only worry if the performance actually causes you a problem. Because fundamentally, if a contract is violated, you have a bug. The most likely problem is the bug is in the caller. It's also possible that the bug is actually in the contract check itself. If that was a more complicated thing that you were checking than is this pointer null, then there might have been a bug in that contract check. But you have a bug somewhere. And so in testing, if you find a bug, you want to get the developer notified as soon as possible with as much information as possible. Break into the debugger. Create a stack trace and a core dump. But provide the maximum information to the developer as quickly as possible. Log custom state if necessary, if that's something to make it easier to track down. What actually was the bug? How did we get here? Why is that value out of range? Why is that pointer null? Why is that the function being called with the precondition not held? What information can we give ourselves as developers to mean that we can find that bug? If you're running this in production code and you have any safety issues with your production code, you now need to change what you do. What you do here should be the safest thing for your use case. In genuinely safety-critical code, that might be trigger the watchdog to reset the system to a known safe state. Because we don't expect to violate preconditions. We shouldn't have got here. Something has gone wrong and we don't know what, because we're in a production system. And this could be bad input. It could be that we've had a hardware failure. We don't know. We shouldn't have got here. And so you say, please, Mr. Watchdog, reset me to a nice state where I know where everything is. I know what all the values of my globals are. I know where I am, and make sure that I can continue from here. If you're not in safety-critical code, then you might choose to do something else. It might be that the safest thing for your use case is not reset everything and start again. It might be carry on limping along because we might continue where we are, having logged that something went wrong, but the consequences can't be that bad because we know in this particular case that the consequences can't be that bad. And often, and in fact, this is the sort of thing often people, if you have an existing system that in practice works fine, nobody reports any problems, everything comes out okay, but you want to start adding precondition checks and things, or an undefined behavior checks, and you find actually there's an out of range thing happens here. It doesn't cause us a problem because the next value you're reading into a vector, it's got allocated memory, there is a value there, it reads it as 0. Yes, it's undefined behavior, but the 0 doesn't cause us a problem. But we'll log that so that we can carry on, and we don't suddenly start breaking people by resetting things when they weren't expecting it. And previously this worked, and so, hey, the new version now crashes and loses my data when the old version didn't because you turned contract checks on? Really? No. So if this isn't a directly safety critical thing, or you're adding it to existing code, then you might choose to do something else. But you need to think, what is the safest thing for your use case? And really think about that. Actually, this is not just, oh yeah, well, no, never mind, we'll just continue. Or, oh yeah, no, we must always do whatever. No, think about it. So, I said undefined behavior is bad. Well, what can we do to avoid it? Well, obviously, there's some simple things you can do. Firstly, initialize all your variables, people. I mean, sometimes, so many people, they just, int I, semicolon. And then they forget to, it's supposed to then call some initialization function that stores the value, but it don't, because there's an if, and it doesn't happen on for some reason that they hadn't thought of, it doesn't happen, that branch doesn't happen, the value doesn't get initialized, it now has a random value, bad things happen. Don't do that, initialize your values. Now, obviously, we're trying, the C++ 26 we have erroneous behavior for this sort of thing. Access an uninitialized value is now erroneous behavior with a defined value that you get to read, but also the erroneous behavior handler gets triggered. So that sort of thing can now be detected, but still, things like undefined behavior sanitizer detect it anyway. But please do that. If you've got a value and you don't want to explicitly check the range yourself, then just use something like at when you call vector.at to check the range for you. It will throw an exception, and you should be handling that. Yeah, exceptions should be expected. So that's then changing undefined behavior from being out of range to defined behavior. Now I've got an exception that I therefore can handle. And then if you rather than using raw pointers, then use spans and string view, so that you now have a range that you can bounce check against. And when you pass that around, it's much easier to pass a single span than it is to remember to pass a pointer and a length and make sure that they stay together everywhere. Use range-based for loops. You don't have to worry about getting the loop condition wrong if you use a range-based for loop. It's these simple things. And likewise, with lifetimes, use RAII. I mean, see, these are just simple and obvious things, hopefully, to everybody, but making sure that we do them reliably and consistently. Yeah, I mean, it's not an exhaustive list. There's obviously loads of other things that we can do too, but these are simple things that we can just do in our code every day. So, I mean, I mentioned earlier about making sure that our block of cheese is thick enough that the holes don't show through. I mean, it is unsurprisingly named the Swiss cheese approach. We're doing our defense in depth. We want to design our systems to minimize the potential for problems. And this comes back to thinking about what the potential inputs are, thinking about where we can go with things, what we're doing, how things. If this module goes wrong, what can we do? So there's things like that in terms of designing the whole system, though, I said earlier about potential for backup systems. So you can say, well, we've got this system, and if that doesn't work, then we can use that one. But you've got to make, it's not just necessarily about having two things. It's about, are they doing the same? Is there going to be a common failure? And if there would potentially be a failure that would cause both of your systems to fail simultaneously, then that's not a good backup. You need to design the system so then there would be the potential things that would cause module A to fail don't affect module B if you're trying to use it as a backup. But then sometimes it's just like, if you change the way your system is designed, then that's now not, some failure options just disappear altogether. If you're passing a plain integer around, then you've got to deal with negative numbers. If you pass an unsigned integer, all your numbers are positive. And so suddenly that changes the way that you're looking at things, by affecting the potential scope of what your things are. If you pass an enum, then it's very easy then to check, is this a valid enum value? Have I got one of the defined enumerators, or have I got an undefined value? And you can write a function that's easy to check on that. And the compiler or static analyzer will easily tell you if you've got a case statement, if you're missing a case statement for one of the enumerators. Whereas again, if you're just passing an integer, then you can't check. It's harder for you to check in code. The compiler can't tell you because it doesn't know what the range of valid integers is for your function. So by doing things, by using the abstraction tools that we have available, using span rather than a pointer and length, all these, using your own custom class to represent something as an entity that then has its own checks that it can do, so that, well, I accept a valid instance of this object, and that means that there's a whole bunch of properties that go with it because I've checked it. So that minimizes the potential for problems. And then use static analyzers. There's a whole bunch of them out there. Coverity, C++ test, CodeQL, a whole bunch of others that I can't remember the names of. Even ClangTidy. ClangTidy does a good job of detecting a whole bunch of things, and it's just free and open source and probably available on just about every platform that's got Clang, which is most of them. So use the static analyzers that are available because they really do find bugs. Admittedly, they do find a fair chunk of things which are false positives. They say, there might be a problem on this line, and you say, no, there isn't. Add a comment to that source line to say, no lint this because I know that this is okay for whatever reason. But it makes you think about the source line. It makes you check your code. Is this really what I intended here? Is it really safe? And that's a good thing, because even though it's a false positive, then it's making you double check, is this what I intended? It's a pain if the false positives vastly outnumber the actual true positives. And certainly with one of the static analyzers that we tried, then the initial version did that, and then they fixed a load of bugs, and then it no longer had quite so many false positives, and that was good. But even so, it's still, it's worth checking. The actual time spent checking your code is worth it if you're caring about safety. And the static analyzers do a lot of that checking for you, and they tell you, okay, can you double check this line? Is it really what you intended? Is really what that issue? When it says you have a potential issue on this line, then it's double check that just to make sure that's what you want. And then tell me if it is what you want, then put a comment. If it's not what you want, change it, do something meaningful. And then having run the static analyzer and said, okay, there's no obvious issues now. Doesn't mean there's no issues, it just means there's no obvious issues, even to the static analyzer. It's not perfect. And so you test it, and test it with potentially problematic input. Things that you've thought through, this can cause a problem. What happens if my string is too long? What happens if I order -1 beers? No. What happens if there's a SQL injection attack? No. I thought there might be a problem. I intended to address it, add a test to make sure that I have done so. Or if you're running test-driven development, do the other way. I can think there's a potential input here. I'll write a test and then make sure the code fixes is there to fix to make sure that that test passes. But either way, add the test. And then for those cases that you haven't thought that they might be problematic, do fuzz testing. Have a generator that generates a whole bunch of random-ish input for your function, for your code. Random config files that are almost correct but not necessarily, or just random garbage, depending. And see what happens. Process with network packets which are either, again, almost well-formed or well-formed with bad values or whatever, or even just random junk. And verify that your code behaves sensibly under that scenario. Because this will help you flush out the things that you didn't think of, the unknown unknowns. The little corner cases where I thought that I was handling that, but actually, if I've got short string's fine, long string's fine, a string that's exactly 32 characters, that's a problem. You wouldn't necessarily have realized that because somewhere you've got a less than or equals, and it was supposed to be the other way around. And you thought you designed for that case, and actually you've got a problem there. So the fuzz test will help you flush those problems out. And then again, use the sanitizers, use the harden libraries. These will help you find them. And by putting all these approaches together, then we make our chunk of cheese thick enough that it's opaque. We can't see through it. There are holes in various points within that chunk of cheese. But because we're doing all the things, then our chances of having a hole that goes all the way through are somewhat reduced. And then, final option, use contracts. Define what your preconditions are, even if that's just in your documentation. Writing a line in documentation for the function. This function requires that you give it a pointer that is not null. That is so useful as a developer to know that passing null is a bad idea. Because people don't otherwise know. Number of APIs, they specify pointers. It's like, well, what happens if I pass a null pointer? Am I allowed? If I say copy 0 bytes from a null pointer, is that allowed? Or is that undefined behavior? And various other things. But by specifying that I've got a precondition, that pointer must not be null, then you can say, aha, I need to check that. I need to make sure that it's not null, even if I'm not intending to do anything with it. If it's trying to be it's an out param that you're not intending to store anything in because I know that nothing bad's going to happen, or I know that the logic path that leads to that being updated isn't supposed to be happening because it's only supposed to happen on Tuesdays and I'm passing in a date that says it's Wednesday, or whatever. But that helps me as a developer if the functions I'm trying to use have preconditions. It then means that they can be checked at runtime if you actually add precondition checks. It means that the static analyzer can potentially check it if you added the right annotations for the static analyzer that you're chosen to use. There is a lot of benefit to be had from those contract checks. So yeah, lots of software has safety consequences, even software that is not safety critical. If you think about things potentially, if you're willing to accept that the things that you might have thought of as security issues, actually, for the people using the software, they often think of that as a safety issue. Then there's often safety consequences in lots of places. And once you've got the thought that there's a safety consequence, then think carefully about what your desired behavior is. What is it that you're really trying to achieve here? If something happens that I'm not expecting, how can I do something that fits in with what my overall state of, intended functionality of the system is? Is there something meaningful I can do for the various sorts of undesired inputs, which hopefully are now expected inputs rather than unexpected? And if we do have a problem, we encounter a problem, somebody's given us an out-of-range value, our sensor's not working, there's been random hardware corruption, this enum, which should have been one of 3 values, actually it's got some random other fourth value, due to random memory corruption. If we can detect that problem, what's the safe behavior for our system? What is it that we should do? And then, of course, used common code patterns. The reason things become idioms is because they're useful. The reason that we have the design patterns as a design pattern language is because they are useful. They help us solve problems by simplifying what we're having to think about. We can say, use a factory pattern here. And then we don't need to think about all the details of that. We need to think about, is that the right choice? We can say, use RAII to manage the lifetime. We now don't have to think about some of the details of that. We can say, okay, is that the right lifetime from here to here? Or do we need to move the lifetime from this block to that other block? Does it need to be a shared ownership and move semantics transfer? But because we've thought about that, we're using the high-level patterns, then lots of the details don't have to matter. We can just think about what we're trying to achieve. And so using span, it simplifies it. We've got a pointer and 2 integers. Is one of them the length? Don't need to worry. We've got a span and another integer. Okay. Now they clearly mean different things. And use our Swiss cheese pattern now, defense in depth. Try all the things. Do them consistently all the time in your testing, in your production code. Do the design, do the testing, do the fuzz testing, do the white box analysis. Put the contracts in. Use the hardened libraries. Use the static analyzers. Do all the things. Because what we're trying to achieve is we're trying to make our code safe. And for whatever that means for the purpose that our software applies to. Okay, so I'm just going to make an announcement here. At the beginning, I said I'm working on the low-level libraries for Toyota, for Waving Toyota, and actually what we are doing is we are making those open source. So our foundation-level C++ libraries for safety-critical software is going to be open source. It's going to be under the Apache license. With the LLVM exception. So you can then just use these in any of your code. Obviously, the public version isn't inherently safety certified. You still need to get it audited and everything. Or you can potentially talk to us if you want to use some of our audit results or anything. But it's there. You can try it. You can use it. It's designed for AutoZAR and MISRA coding guidelines, which means it's based on C++ 14 and 17. Sadly, the MISRA guidelines, even the 2023 guidelines, don't cover anything more recent than that. So that's where it's designed. Actually, because we're trying to use it on embedded systems, then it includes a subset of the standard library. And so if you're on a system which is restricted, then there's potential to use that there. We've got various things with no dynamic memory allocation, so inline vector and map and string, which the storage is there within the object rather than allocated on the heap. So it's like in-place vector is the C++ 26 version of our inline vector. And then we've also got some backports of new stuff. We've got a string view, we've got MD-span, because we're stuck with old versions of the compiler. That doesn't mean we have to use old library stuff. So yeah, this is going to be open sourced, and I was hoping that I'd be able to give you the URL for download today, but due to admin reasons, then that didn't happen. But any day now, as it were, it will actually be available. Yeah, and like I said, we use preconditions all the time, and ours are always enforced. And then another announcement, Jens mentioned my book. If anybody hasn't got a copy, then Manning are offering a 45% discount for attendees at the conference. So there's a URL on the slide, and then you need to use the meeting CPP 25 code. So yeah, if you want a copy of that, obviously it's not about safety, it's about concurrency, but hey.